Welcome back to Learning with Merit. Today we're going to talk about data encoding. And basically you can think of it as how are we going to understand a computer? How does the computer understand data? And how do we go back and forth between ways that we can understand data and ways that the computer can understand data? For example, a great example here is you'll see Welcome back to Learning with Merit. But the computer sees something more akin to these letters and numbers over here. And you may not understand them right now, but by the end of this video, you'll have a better understanding of what you're looking at here and even ways that we can edit it to do different things. So the first thing that we are going to do, we're going to come over here and we're going to take a look at some data encoding. So we are going to cover the decimal system. We're going to cover the binary system, how to convert, hexadecimal, how to convert from there, then something called ASCII and UTF-8, and then a hex editor like you just saw a second ago. So let's start with the decimal system. So this is our base 10 system, meaning everything's based on tens. It comes from the Latin decimus, and it means tenth. And then we always have 10 digits, 0 to 9, like you see right here, and then 0 through 9 right there. And that is 10 digits. And that can go in every spot. So here we can have 0 through 9 in the 1 spot, 0 through 9 in the 10, 0 through 9 in 100, 0 through 9 in 1,000, and so on and so forth. And you can see we're base 10 here. So this is if we do powers of 10. 10 to the 0 power is 1. 10 to the first power is 10. Second is 100. Third is 1,000. Fourth is 10,000. So on and so forth. And then if we look at the decimal part, so if we're going down to the fractional pieces, we'll see that it's 1/10, 1/100th, 1/1000th, and these are negative as we're going down. Okay, so this is our basic number system. This is the one that we are all used to. Okay, but it's not the only number system. And in fact, you may go an entire life without having ever looked at some of these other number systems, but there are literally infinite ways that we could represent numbers and the ways that we use them. So one example here, you already probably understand, this is pointless to go over, right? 156, what does it mean? Well, it's 1 100, it's 5 tens, and 6 ones. And when you put that together, we understand 156. All right, but the computer's not going to understand that as easily. The computer needs a different way of looking at numbers. There's actually several different ways that the computer looks at numbers. This is one of them. It's called the binary system. So computers only understand ons and offs. Really, when you break a computer down to its most simple components, it only understands on and off. And so we need a way to represent and do things with just ons and offs. So enter the binary system. So bi literally means twice, double, or two. And in this case, it means we only have two values. We have a 0 or a 1 value. So instead of 0 through 9, each place can only have 0 through 1. So if we look at this, instead of a 1s, 10s, 100s, we have a 1s, 2s, 4s, 8, 16s, 32, 64th, and 128. And that goes from 2 to the 0 to 2 to the 7th. And you'll notice that we've replaced the 10 with a 2. Our base is now a 2 instead of a 10. And then same thing, our decimals are a little bit different than we're used to because it's 1/2, 1/4, 1/8, 1/16th, as opposed to 1/10, 1/100th, so on and so forth. So we easily understand the decimal system, but computers operate in what we call bits. And a bit is a 0 or 1, a on or off, a powered or unpowered, a true or false, something like that. So if we look at bit down here, we have the definition, the smallest unit of data a computer can process or store, and it's represented as a 0 or 1, a yes or no, a true or false, or an on and off. And this right here is very important, the true or false. This is called Boolean. Right? It's called a Boolean. And so basically a bit is where we deal with our Booleans, and that's why Boolean algebra and Booleans come up so much in programming, is we have those 1-bit Boolean zeros or ones, trues or falses. Now if we take those bits and we organize them into groups of 8s, and there's actually a really good reason for that, but I don't want to go into it here. Okay, but we take that and we organize it into a group of 8, and we have something called a byte. So 8 bits are a byte. And of course, you can go into the metric system prefixes and use pretty much all of those. Megabyte, you've probably heard of. You've probably heard of megabyte. You've probably heard of gigabyte, kilobyte, terabyte, perhaps. These are all large numbers of bytes that you may be dealing with. In fact, most hard drives now are gigabyte or terabyte drives. So very large amount of data there when it comes to bytes and bits. So if we look at one bit of binary data, we could call that just a 0. We could call that just a 1. We could have 8 bits or 1 byte, and that could be all zeros. It could be all ones. It could be any combination of zeros and ones. Okay, so here we have 8 bits of binary data with some ones in it that time. And I have split it up here in the middle, so you won't always see it split up like this, but sometimes you will see it split up with an extra space here just to make it a little easier to read, because when you get all those zeros and ones stuck right together, as you'll see down here, it can be a lot harder to read. So let's take a look at some examples here. First of all, the decimal number 0, so what we're used to, 0 is also 0 in binary. Okay, if we take it as a byte, it's just a bunch of zeros. Okay, so 8 zeros there. The number 1, also very simple. It's just 1 in binary as well. Okay, if we take it as a byte, it's going to have 7 leading zeros. Okay, and remember, just like we could have leading zeros in the decimal system, but they don't mean anything, right? So sometimes in computers we need the leading zeros because they represent a non-value, right? Let's look at the number 5. The number 5 is 101. It may be a little confusing why it's 101. Well, that's because in the 4's spot we have a 1. That gets us up to 4. In the 2's we have a 0, because that if we added 1 there, that'd get us to 6. We don't want that. And we have a 1 in the 1 spot. So 101, that means 1 4, 0 2's, and 1 1, and that gives us 5. If we take it as a byte, you'll see that as well. The number 10, basically we have a 1 in the 8 spot, we have a 1 in the 2 spot, and that gets us to 10. 42 is getting a little more tricky here. So we have a 1 in the 2 spot, we have a 1 in the 8's spot, we have a 1 in the 32 spot. So 132 plus 8, so 32 plus 8, let me be clear, 32 plus 8, not 132. So 32 plus 8 is going to give us 40, plus 2 will give us 42 there. 100, so we have a 1 in the 4 spot, and if we keep counting out here, so that would be 8s, that would be 16s, that would be 32. Don't want to mess that up. That would be 32, and then the last spot out there would be 64. So 64 and 32 would give us 96, plus 4 gives us 100. All right, and I'm not going to go through all these. This one's actually pretty easy because there is a 128th spot. If we go back up here and look at that. Right there, 128. And then 255, I wanted to show you this. 255 is the largest number that can be represented in one binary byte. So in 8 bits, 255 is the largest number that can be represented. So that would be 0 through 255, so that makes 256 possible numbers in a byte of binary data. So let's take a look here at converting, and we've got 2 different ways we're going to convert. We're going to take it from decimal to binary, and then from binary to decimal, and we've got some steps here. And there's lots of different ways you can do it. You could sort of do what I did up here, where I sort of counted the places and added them all up. There's also a little more of a trick down here that we're going to follow. So converting from decimal to binary, that's what we're going to start with first. So we're going to divide the decimal number by 2 and write down the remainder. So let's look at our example down here and follow along. So it says convert decimal 13 to binary. So what we do is we divide 13 by 2, and we get the number, let me really zoom in here, we get the number 6. And with a remainder of 1, because 13 divided by 2 is 6 with a remainder of 1, so we write the number 1 down. Now we take that 6 and we divide it by 2, and we get the number 3 with a remainder of 0. So we write that 0 down to the left. That's really important. It's to the left. Then we take that 3 and divide it by 2 right here. We get 1 with a remainder of 1, so we write that 1 to the left. We take the 1 right here, remember it's this one, our quotient, and we divide it by 2. So that second step I keep doing here, it says use the quotient from the previous division, divide by 2, and write down the remainder. So we're doing the same thing. We're taking that quotient like we did here, taking that quotient right there, and then when we get to 0, we're going to repeat until the quotient is 0, writing the remainders from right to left. Okay, so we start on the right and write through the left. So we eventually take that 1, divide by 2. Well, 1 divided by 2 is 0 with a remainder of 1. So we get 1, 1, 0, 1. And that is 13 in binary. It's a very simple way to do it, and you don't really have to think that hard about what you're doing. You just keep dividing until you finally get to 0, and then you should have your decimal number there. So if we represent it as just bits, it can be like this. If we represent it as a full byte, we could write it like this. Either or will work just fine. Okay. The other way you can do it, of course, is if you sort of memorize the places like we do in our decimal system, because we know it's ones, tens, 100s, thousands. We know that. And if you work with binary for a while, you'll know it's 1s, 2s, 4s, 8s, 16s, 32s, 128s, and you'll remember that. But for right now, this is probably the easiest way for you to do it. So let's take this and let's do this example problem here together. So 230. This is a little bit more difficult than doing 13. So you may want a calculator. And we can pull up a calculator here and work with it. So 230. So we're going to do, let's see, 230 divided by 2. Well, look at that. That's 115. So we're going to write down 0. All right, now we're going to bring our calculator back up here. All right, so now we need to divide 115 by 2. Now the good thing is we know that if we get a decimal there, then we know the remainder is 1, because if you're dividing by 2, there's only one remainder there could be. It's either 1 or 0. Those are our two possible remainders. All right, so we get 57 with a remainder of 1. So I'm going to write down the number 1, and we're going to keep going. All right, so we need to take 57 and divide by 2. And we get 28 with a remainder of 1. We're going to do that. Now we need 28 divided by 2. That's going to be a 0, since there's no remainder there, no fractional part. So now we have 14 left. So we divide by 14, we divide by 2 again. We get 7, so no remainder there. Oops. Gotta keep going. Now we divide by 2. 7 divided by 2 is, of course, 3 with a remainder of 1. So we write down the 1. Now we have 3 left. We divide by 2 again. You get 1 with a remainder of 1 there. So we're going to write down another 1. And then we need another 1 because 1 divided by 2 will give us 0 with a remainder of 1. So there we go. So how many numbers do we have here? If we separate that out, we have 8. So if we do this the other way, just to check our work here, the spot right here, I gotta quit doing that. The spot right there is 128, so it's 128 plus, the next spot is 64, so plus 64. Next spot is 32, so plus 32. This is the, let's see, that's 1s, 2s, 4s. So let's see, we're going to add 4 and add 2. And what do we get? Lo and behold, 230. So that converted 230 to binary for us very easily. All right, so we're going to come back to that and do some practice problems later. So let's take a look now at how to convert from binary to decimal. So this one's a little bit more complicated, but you can sort of do what I just did there. If you remember the places, you can just add up all of those numbers. And that's one way to do it. This is another way for you to do it. So it says find the leftmost digit that is, or sorry, leftmost bit that is equal to 1 and multiply by 2. So if there's leading zeros, it means skip the leading zeros. That's what this means. And leading zeros are zeros that come before a 1 in binary. All right. So we're going to find the leftmost 1 and multiply by 2. So here we have 101, which we know to be the number 5 from our example earlier. We are going to take this leftmost 1, we're going to multiply it by 2 and add the next digit. All right, so it's going to be 1 times 2 plus 0, and that's going to give us 2. Now we're going to take that number, multiply it by 2, and add whatever the next digit is. So in this case, we are working with this number 1 right here as our next digit. So it'll be 2 times 2 plus 1. So 4 plus 1 will give us 5. All right. And so if we have a much larger one, we're going to do something similar. So here's our first digit. We're going to convert this to decimal. So here our first digit is 1, so we do 1 times 2. Our next digit is also a 1, so we add 1 to it. So there we have 3. Then we're going to go on 3 times 2. Our next digit is a 0. So we add 0, we get 6. 6 times 2, our next digit is a 1, so we add 1, and we get 13. So 1101 in decimal is 13. So 2 different ways you could do that. You could also just say, okay, so that's the 1s, that's the 2s, that's the, whoops, gotta stop doing that. That's the 4s, and that is the 8s. So it'd be 8, 4, and 1, which would give us 13, okay, if we add them up. And if you need proof, 8 plus 4 plus 1, 13. Okay. So let's take a look at maybe a little harder example here. We're going to do this number here, and we're going to convert it to decimal. So bring this over here just in case we need it. All right, so we've got our leftmost 1, and we're going to multiply it by 2. So 1 times 2, our next digit is this one right here, so we're going to add 1. Now we're going to multiply that by 2. Our next digit is a 0, so we are going to add 0. We're going to multiply that by 2. Our next digit is a 1, so we're going to add 1. Multiply that by 2. Our next digit is a 1, so we're going to add 1. We're going to multiply that by 2, add 0, and then multiply that by 2. Okay, and we get 58 so far, but we got to multiply by 2. One more time. See, we get 116. Let's make sure that this is actually right. Make sure we did all our math right. So another way to do this, so we're checking for 116, is we can say, well, that's the 64 spot, so 64 plus, and then we have the 32 spot, plus 32, and then we have, let's see, that's 1s, 2s, 4s, 8s. So we got an 8 and a 4. So plus, let's see, plus 8 plus 4. See if we got two different answers here. Make sure we did everything right. So that's a leading 0, so that would be 64, 32. That would be 16, that would be 8, that would be 4. So we should see 108. We should see 108. So let's make sure that we did this right. So we take 1, multiply it by 2. We add 1, multiply that by 2. We add 0, so we can skip that. We're going to multiply by 2 again. This time we need to add 1. Then we multiply by 2. We still need to add 1 again. Then we multiply by 2. Then we multiply by 2. And there we go, 108. So I must just have messed up on my adding there. So that's why it's always a good idea to check yourself. So like I said, there's two different ways to do it. And if you don't like this whole add one, and I'll be honest with you, I don't like the add one sort of system either. I just prefer to know the places and add them up. And so if you like that better, use it. It doesn't matter how you get to that answer as long as you have a way that works for you. If this little trick works for you, do it. If remembering the places works for you and just adding them up, do it. Okay, whichever one works. All right, so let's talk about the hexadecimal system now. So now that we know how to do binary, right, and it's just a slightly different system than what we're used to. We just sort of change the places, but everything else still works the same. We're just changing the places of how we can represent those numbers. So instead of 0 through 9, we've got 0 through 1. Well, let's say that maybe I wanted to reduce the amount of space that my numbers take up, right? And so instead of something less than decimal, I wanted something larger than decimal, like hexadecimal. And the great thing about hexadecimal, which is a base 16 system, is that it's also in line with binary. So binary is base 2, right? And we'll see everything's divisible by 2 here. Well, if you look at hexadecimal, everything is divisible by 2 as well. And so that allows us to very easily go back and forth between these two, and it also allows us to represent a lot more data, such as in binary bytes, in less space. And I'm going to show you how that works here in just a second after we get an understanding of hexadecimal. So hexa means 6, and you've probably learned that from like a geometry class. If you haven't had a geometry class yet, hexa means 6, like hexagon means a 6-sided figure. And then deci, of course, meaning 10. So if you take 6 and 10, put it together, we get 16. Now, a issue with this is that once you start trying to represent 16 digits, you don't have enough number digits like we think of them. So we've got to come up with other symbols to represent those other numbers. So what they did is they used 0 through 9 just fine. But to get through from 10 to 15, we introduced letters from the alphabet. So we used A, B, C, D, E, F, and that would be 10 through 15 respectively. So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And just like 0 through 9, right, we don't go to 10, right? So we're never actually hitting 16 here. Just like also in binary, we're never hitting the number 2, okay? It's zeros and ones. That's what we can represent. I didn't go quite as far out with hexadecimal because we're not going to go out quite as far with hexadecimal in most of the things we're dealing with. And I wanted to show you just how big it gets as you go through hexadecimal. So it starts with ones, and there's 16 places, and then we get to the 16s place, and you can have, of course, 16 numbers there, and then the 256th place, and of course you can have 16 numbers there, and it just keeps getting bigger and bigger and bigger. And by the time you get to 16 to the 4th power, we're at 65,536. which is 2 to the 16th power, by the way. So a very large number there. The good news is that hexadecimal, while it's a little more complicated, we're mostly going to stay right here in what we're doing for this class. And of course you can see if we were using decimals, you would have 1/16, 1 256, 1 4096 as we were going. Okay, the trick here is remembering that A is 10 and F is 15 and all the little numbers in between, and keep that in your head. This is, this is not letters. These are meant to represent numbers that we understand in our decimal system. It's just conversion. Okay. Now, they can be uppercase or lowercase. So just because I've represented them in uppercase here doesn't mean they can't be lowercase when you see them. I just tried to pick the one that I felt like I've seen the most in my working with hexadecimal to try to make it as comfortable as possible for you when using it. But you will see them in both uppercase and lowercase depictions. So you will also often see them written with a hashtag or hash symbol or pound sign, however you talk about it. Or in Python and some other places, you also see it with a 0x in front of it. So these are things to indicate that the number is not decimal or binary. It is in fact a hexadecimal number. All right, and that's actually, you may not think it's important right now when you're just looking at it, but when you look at some of these numbers, you're going to be like, okay, is that decimal or is that hexadecimal? And we need some way to distinguish between the two. So these are both the same number here, 00 or 0x00. Now Python uses 0x, and since we've been working in Python in class, I plan on using Python sort of depictions here. But I do want you to know about the other way as well, because you will see them occasionally. All right, so let's look at some examples here. Of course, we're going to start with the 0 example. 0 in hexadecimal can look either one of these two ways. This is the way I'm going to stick with, mostly for now. They're highlighted. The number 1, of course, is 01. 01, very easy. 5, 05, 05. When we get up to 10, here's where things get a little different. I used lowercase this time to help you understand that it can be either. And so 0A would be the number 10 in hexadecimal. So since A is 10, we just have 10. No fancy conversion there. You just have to know A is 10. Use that little chart. 42, it's a number we used earlier. So 42. In order to get to 42, how many 16s are there? Well, we'd have to sort of divide it by 16. What you'll find is that 2 16s will go into it pretty easily, and then there is 10 left over. So 16 and 16 is 32. That's where this 2 comes from. 16 and 16, there's 2 of them. And then A is 10, so 32 and 10 would give us 42. Here's a great example of why we need the depictions of the hashtag or the 0x there. 64, is it decimal or is it hexadecimal? Big difference between those two numbers. So if we look at this, the 6 is how many 16s there are, and then the 4 is the number 4. So 6 16s should get us to 96, and then 4 would get us to 100. Same thing here. So we have 0 in the 1 spot. We have 8 in the 16 spot. So 8 times 16 is going to be 128. And then the largest number that we can represent in one hexadecimal byte is 255. So 0 through 255, that's 256 possible numbers, but the largest number is 255, and that is 2 capital F's right next to each other, FF. That'll get us the number 255, and there is actually a reason why I bring that up. And if you study further into programming and computing, you'll start to understand why 255, 256 come up a lot. So let's look at converting from decimal to hexadecimal. So this is basically the same thing that we followed with decimal to binary. You're going to divide by 16s, write down the remainder, okay, get the quotient, and keep going. So let's just do this one real quick. So we're going to convert 24, the decimal 24, to hexadecimal. So we do 24 divided by 16. That gives us 1 with a remainder of 8, so we write the 8 down. Then we do 1 divided by 16 here. That gives us 0 with a remainder of 1, so we write the 1 down. So 24 in hexadecimal is 18. 1/8. Now, you will hear people say 1/8 as opposed to 18. But you did just hear me say 18 there. I wanted to point out a very clear distinction. Most people, if they are speaking about hexadecimal, will say 1/8 as opposed to 18 to make it clear that we're talking about hexadecimal. Okay? Because if we say 18, it makes you think decimal 18. Whereas 1/8 is sort of a signal, it's a little different than that. So here's another great example. Let's convert 255. Even though I've already told you what 255 is, let's convert that. So if we do 255 divided by 16, we get the number 15 with a remainder of 15. Well, what is 15 in hexadecimal? It's the letter F. So we write F down. Then, here's our 15. We're going to divide that 15 by 16. We get 0 with a remainder of 15. So we write that F down. And we get FF. So, the decimal 255 is FF. So let's do our little example here. 165 to hexadecimal. Let's see if we can get that figured out. So 165 divided by 16. Now here's where we come up with a little bit of a dilemma. So last time we knew it was always a remainder of 1 or 0. We don't know that with this. So how can we figure out what's left over? Well, you see this little fraction part right here? This will tell us how much of 16 is left over, or the remainder every time. So we've got 10 here, and we need to figure out what the remainder is. So I take 16 times 0.3125. 0.3125. And it looks like our remainder is 5. So I'm going to write that down. Oops. So our remainder is 5. Now, we need to take the 10 that we had. So 10 right here. So I'm going to make this a little bit bigger actually. So now we do 10 divided by 16. Well, 0.625. Well, here's what I'll tell you. 10 divided by 16 is 0 with a remainder of 10. What is 10 in hexadecimal? That is the letter A. So I'm going to write the letter A down. So let's think about this. A is 10. What's 10 times 16? Well, that's 160. And then what's 5? Well, it's 5. So that's 165. So 160 plus 5 gives us 165 in hexadecimal. Let's make sure that it's clear, though. Let's use 0xA5, and we know that is a hexadecimal number. So let's look at going the other way now. So starting from the right, we are going to multiply the digit by 16 to the 0. So this may be real confusing to us, but I'm going to try to simplify it for you. We're converting from hexadecimal to decimal. Basically, what this is right here is a long-winded way of saying you have to know the places. So there was a trick. There was a trick with binary, and maybe you liked that trick really well. But there's not really a good trick with hexadecimal. We just have to know the places. So what we're doing here, down here, is we are multiplying by the places to figure out our total answer. So if we take A3 and we try to convert it to decimal, well, 16 to the 0 is the ones place. So it's 3 times 1, and we get 3. A is in the 16 to the ones place, or the 16s place. So A times 16 is 10 times 16, so we get 160. If we add those two things up, we get 163. So let's look at this one. Here's another example. This is a much larger number. The good news is most of the time you're going to be converting numbers like this, so your life should be fairly easy. But in this case, let's take it one step further and actually convert a harder number. So we have a 0 in the ones place, so it's 0 times 1. That gives us 0. We have a 9 in the 16s place, so it's 9 times 16. We get 144 for that. We have C, or 12, in the 256 place. So that would be 12 times 256, which gives us 3,072. And then in the 4,096 place, that's a 1 sitting right there. That's a 1 from right there. So we get 4,096, and we take that, add across, and we get 7,312. So this number, 1C90, or 1C90 in decimal, is 7,312. So let's take this little system and see if we can convert real quick. We have the number, the hexadecimal number 6E. 6E. So let's do the math here. We have a 6 in the 16 spot. So I'm going to do 6 times 16. And that gives me the number 96. E is 14. So I'm going to add 14. And that gives me 110. 1, 0, like that. So it's not hard to convert. You should use your calculator, make your life easy, and just follow the simple little rules and try to use your little chart of the places to help you figure it out, much like you would with decimal. All right, last thing we're going to talk about here is something called ASCII and Unicode. So the American Standard Code for Information Interchange, golly, that's a mouthful. That's why everyone calls it ASCII. Right, and then we have Unicode Transformation Format, or UTF, and in this case we're going to talk about UTF-8. There are other versions, but we are specifically going to talk about UTF-8. So ASCII is the standard data encoding format for electronic transmission of text. That's a mouthful, and it uses only 7 bits. So it doesn't use all 8 bits. It uses 7. Now, this was how we were able to translate from the binary, from what the computer understands, to text that we can transmit. So the computers have to share binary, but we need to look at text and read it, right? Because we don't read binary that easily. So this is how the computer is able to understand the text and the other characters, because we basically have a way to translate back and forth. All right, the computer sees the binary, we see the text or the character, whatever it is, right? And we're able to go back and forth, transmit the information. And there's a bunch of different ways that we encode it, or, literally you have to think of it, we code the text in different ways. It may be a number and we understand that number, but down here we have a key. And the key is basically how we understand the different code, the different numbers or ways that we represent that letter, that character. Okay, those are the different ways that we do that, and that allows us to understand as we go back and forth and change the data and do all that sort of thing. It gets really confusing if you don't have a key for it. So we can also use a tool called a hex editor to see inside the bytes of a file. So I talked about bytes earlier, and talked about hexadecimal, talked about binary. All right, if we want to see the bytes of a file as opposed to what it's been translated into for us to read, we can do that. We just have to have a little tool for it called a hex editor, and we're going to look at that in just a second. UTF-8 is what extends that ASCII character set. So basically it doesn't change anything, it just extends it, and instead now uses all 8 bits which allows up to 256 different characters. And of course, we have much larger sets than that to represent things like emojis and all the stuff that we play around with nowadays. But this is the easiest way to step into this world is with something simple like UTF-8 and ASCII. So we can represent all the printable ASCII characters as well as some non-printable characters with UTF-8, and it is very commonly used today. But of course we want to learn about ASCII. So there's a reference here that I've linked, and of course you'll have access to this stuff. But if we look at this, you can see that here's the binary for an exclamation point. And if we look for our letters, we start at decimal 65, and we have the binary for that right there for A. And of course, you'll see that uppercase letters are coded differently than lowercase letters. And I've mentioned this before in class that that makes a difference to the computer. And it is because the binary for an uppercase A is not the same as the binary for a lowercase a. And the computer does not understand that they are related. It just sees two different binary numbers. And so it's a very interesting thing, and you can look at this and you can see even some of the other things. For example, a space character. All right, in hexadecimal it's 20. In binary it is 1 with 5 trailing zeros, and we have some different ones that you can see in here. Line feed and new line character, we will see. Let's see if I can find the new line character. Where'd it go? Missed it. Found the line feed. Anyway, it's in here. Oh, carriage return. There we go. So carriage return, all right, and line feed are how we get a new line whenever we're looking at it in something that's reading text for us. And of course, I have a link here to a table that you can look at if you're interested, especially when you're trying to convert between these. So if I open this up here, you'll see, here we go, we've got UTF, and I've tried to limit what you're looking at and make it a little simpler for you. Decimal, hexadecimal, binary, and it explains what they are here, and of course their characters and everything. And then this is the UTF-8, this is the ASCII, and they're pretty much identical because UTF just extends ASCII. And then I added some of the control things that you have there. So anyway, something interesting to look at. It's a nice little table that you'll play around with, be very helpful. And of course you can find a lot of this stuff at W3 Schools. Very good website. All right, so let's take a look at a hex editor now. So you may notice that these are, and I've been saying hex a lot, you may notice that this is hexadecimal, right? And it's because each one of these, because there's only 2 of them, they're a byte. That's right. So a byte, or 8 bits of binary data. Right? And hexadecimal is a lot easier. If this was all binary, it would be nearly impossible to read. It's hard enough to read as it is, but we can actually look at this now and mess around with it and see some things. And you can see, welcome back to Learning with Merit, well, 57, okay, or 57 in hexadecimal, as I should say, is a capital W. 65 is an E. 6C is a lowercase l. Right, and so on and so forth. You'll see, hey, every time there's a space, that's a character too. So 20 is the space character. So every time 20 shows up, we've got a space. So it's a very interesting thing to look at. So I've added some files that we're going to look at. One of them is I've added all of the different characters into a file. So if I click on if I click on open file here, I have a couple of files. I have ASCII.txt. I'm going to open this up. And look at this. So if we look at this file, we have 61, 62, 63, 64. They're all in order, and you'll notice that's the alphabet. And then you'll see 0D, 0A, 0D, 0A. So that's where a new line is happening. So we have a new line feed, 0D, and a carriage return, 0A. And we have 2 of those, and that gets us a new line. So 0D, 0A is going to a new line, 0D, 0A is going to a new line. So these are separated out by an extra line. Okay, and I can actually show that to you. If we go and open the folder and look at the file, I'll open this with the notepad editor, but you'll see, so we're at the end of this line, we go to a new line, and then we go to a new line again. So that's where that 0D0A is coming in, right? And then you'll notice there we're starting with A. So that's 41 or 41, 42, 43, 44, right? And these are all the uppercase letters. And then lo and behold, we have that 0D, 0A, 0D, 0A. Got that new line with the extra space, right? So here we are. 0D, 0A gets us here. 0D, 0A gets us there. And then we have all of these special characters. So the special characters start right here. So 21 is a special character, is the exclamation point, or 21. 40 is the @ symbol. 23 is the hashtag, right? And then we have some example text down here at the bottom, and of course you'll see that 20, 20, 20, that's our space character showing up. And then there's a 0D0A, a 0D0A, 0D0A, so you know there's a bunch of new line characters and feeds. Now, these are not periods. These are not periods. These are extra spaces or new line feeds and carriage returns. Carriage return actually comes from typewriters. And I know that most of my audience probably did not grow up in the typewriter era, as did I. I did not grow up in the typewriter era, but But I do know about typewriters, and they had a carriage return. And so, you know, you hear that tap, 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 ding, and then it rotate back to the beginning. All right, that's our carriage return. And so that's where that came from. The new line feed and the carriage return is left over from typewriting. Of course, if we look at some of these, we have some extra little tools. There's a bunch of information over here. It'll tell you different ways that it may be interpreted, that data. So like 8-bit integers, 16-bit integers. If you know what integers are, those are whole numbers, right? So we can see 3b is like 59. Let's see. 20 is 32, right? It's doing a little bit of conversion for us, making our lives easy. But the computer sees the binary, which can be represented as hexadecimal here. And if you're wondering what's going on here, 10, 20, 30, that's hexadecimal. So there are 16 bytes in each one of these lines for us. So this would be 71 here would be the 16th byte, or excuse me, the 17th byte, because 0 through 15, right? So 0 through 15, so this would be the 17th byte here, and then we would keep going, right? So on and so forth. You can add more bytes, play around with this. But the cool thing is being able to see the actual bytes that the computer sees whenever it sees this file. There's one last thing I want to show you, and this is going to be more of a demonstration than an explanation. But we also have a little binary message challenge that I'm going to provide that'll be there for you to convert from the binary. And the last thing I want to show you is something very interesting that you can actually do with Python. So we come here to our shell, we type out Python, and just hit enter. And I just want you to watch and see what's going on here. thought you might think that's kind of cool. But that's all I'm going to say about that one. Well, that brings us to the conclusion of our video here. Of course, we talked about hex editors. We talked about different data encodings, including binary and hexadecimal, and how to transfer yourself between the different values. Of course, binary, hexadecimal, ASCII being very important, because how do we get from zeros and ones to text? That's going to be ASCII and your UTF-8 encodings, and that way eventually it all gets translated into zeros and ones and bytes, and every file you look at has bytes. You look at a picture file, it's going to have bytes, and there's going to be information in those bytes that tells it that it's a picture file and how to read that data. And if you have the right type of program, it can read that data and render onto your screen a picture with those bytes. So a very interesting way to think about things. And it's the step that we take from the ones and the zeros to stuff that we can use every day. All right, I hope this was helpful. And of course, if you have any questions, you can ask them in class. Thank you for watching.